Justin Pierel is our last speaker. Is at Space Telescope Science Institute, has experience with finding actually lens supernovae, or at least one, I'm not sure, yeah. And Rubin Roman Synergies. So this is the first talk about synergies, and we will hear tomorrow and this week much more of these types of aspects. So all set, and Justin, please take it away.
Good. Yeah. All right. Thanks, Simon. All right. Does this work too? Great. Okay. Well, I was lucky to go last and not have to go over any background. So I knew that at the beginning. So I'm going to talk about Rubin and Roman synergies and the current prominence of cluster lens supernovae. And I did this before. Okay, before I knew everyone was going to do background, so I knew Nikki was going to, so I specifically highlighted hers, but I'm glad I did because this was quite a cool watercolor way of doing this. So thanks to Nikki and everyone else for doing background this morning. I'm not going to do it at all, and instead I'm going to talk about the so many cluster lens supernovae, so many when your sample is this small at least, why that might be, and then I'm going to dive a little bit into analysis of Supernova Requiem, which is the most recently published discovered gravitational lens supernova resolved. And that's kind of cool. Not a lot of those out there. And then synergies between Rubin and Roman is how I'll close on this. So this is our current distribution of gravitational lens supernovae. You can see we're complete to Redshift 2. And it's going pretty well so far. All right, so there are two more coming, Pat Kelly in prep. They're both cluster lens supernovae. So that brings us to 4 of the 5 lens supernovae that have been found in clusters, spine clusters, I should say. So that's kind of interesting at this point. It's obviously small statistics, but what can we start thinking about why this might be happening? So, maybe it's just that we look at clusters a lot. Look at James Webb, the first image comes of a cluster, right? And we pay a lot of attention to clusters. It gets a lot of data. There's relatively few of them. And so we put a lot of time into the ones that we know about. So, maybe we're just watching a lot. And so we happen to be catching them. Magnifications tend to, on average, be higher. So, maybe we're just catching more in our magnitude limited surveys, possible. The image separations are higher. So in terms of the image multiplicity method of discovering lens supernovae, we're maybe just more likely to be finding them in the cluster scenarios where the image separations, as you'll see, are usually quite larger than for galaxy scale. There's also just lots of galaxies behind clusters, as we see with the James Webb images in particular. So maybe we're just sort of looking at a relatively small number of clusters compared to galaxy scale lenses, but there's a bunch of galaxies back there. So, maybe it's just a numbers game. Maybe it's just chance, maybe the next 10 will all be galaxy scale lenses and we just happen to be finding a lot behind clusters. It doesn't really matter. The point is that the Rubin will be observing these, and since we've been finding them, it makes sense that we will likely continue to find them. This was shown once before, but a Tanya Petruszewska 2020 work on 5 well-studied clusters to show that these alone should, on average or whatever, produce about 1 lens supernova on average between the 1A and core collapse over the full 10-year survey. That's just 5. So I think, as whoever brought this up before said, this should be a lower limit, and I agree. This is a eRosita all sky survey prediction of clusters, but you can see, the expectation is there's quite a few low redshift clusters, and so LSST, even just on in its not all sky survey, will still find quite a few of these, and so 1 in 5 clusters, so you can sort of get the idea that will scale up. And while, the idea in general up till now has been galaxy scale clusters will provide us the majority of our lens supernovae. That has been the thought for a while, and so far that has not panned out. And so, although I agree, it makes sense. We expect that'll happen. Since up until now, the clusters have provided quite well. I think it makes sense to keep looking at these going forward. And not just numbers, there are parameters related to these, as I'll get into, that make them desirable as well. So the current published sample, I'm not going to obviously talk about the new ones. Refstall in 2014 was the first resolve one, of course. Nice 4 initial images, and the 5th provided a time delay of about a year, and that should be coming out any day now on the H0 inference. And a year is a good length time delay. That's as you'll see, as I'll talk about a little bit, that's sort of a nice sweet spot. And for each of these, I'm just going to kind of place them in this little table of what I'm going to call positive characteristics. And by that, I just mean, not essential for cosmology, but things that are nice to have. So large angular separation obviously is nice because we can resolve the images easily, either from the ground or with space-based telescopes, of course. The long time delay is, again, not critical, but it is the relative uncertainty on the time delay that contributes to the Hubble constant. So if you can measure time delays to within 1 day, but your time delay is 10 days, then that's a 10% uncertainty. But if it's 100 days, that's a 1% uncertainty for the Hubble constant. So the longer the time delay, sort of the better, but there is a limit to that, as I'll mention. So Refstall, of course, with a year time delay and obvious large angular separation fits like this. It was a 1987 A-like core collapse supernova, not a 1A. Why 1A? Well, in addition to a couple things that have come up today, including, being able to infer an intrinsic luminosity and perhaps, do things like break the mass sheet degeneracy. It's also just a slightly easier, modeling capability, a shorter time scale, a sharper peak. So overall, your uncertainties for cosmology will be lower, in addition to all the things you can do with inferring an intrinsic luminosity. So great if it was a 1A, this one was not. IPTF16GU was a 1A, but as we saw, it has time delays on the order of a day, making it very difficult to be used for cosmology. And the angular separations are, as we saw, again, were not resolved from the ground initially. So yes, but no. Okay, so that brings me to Supernova Requiem. This was initially discovered by Gabe Brammer in 2020 in archival HST data from 2016. So you can see on the right here is the initial discovery. It's pretty red in 2 images and blue in the middle image here. And then this is our template, but it came later, image from 2019. And you can see again that this is a cluster lens supernova. And we'd like to put that in this little grid here. So one, you can just tell right off the bat, this has a large angular separation, so that's great. So a little bit about what we learned from the cluster itself on this. Well, this was a Johan Richard effort to do the initial lens modeling for this. There is more to be done. I don't think anyone's currently doing it, but there's more projects there if anyone's interested. This was lens tool constraints from a combination of the HST and Muse data. So the constraints basically included the images of the host galaxy for the supernova, the location of the supernova itself, and then there was also spectroscopic redshifts for this, whatever this 3.3 galaxy, 3.1, 3.2, 3.3. So this was a 0.76 galaxy. So those constraints basically gave us some models of the 3 images here. So I'm putting this side by side to show that this down here is the first image, and then 2, it goes with the middle, and then 3 is this sideways arc here. So you can just see it side by side. The H-band actual HST image is on the left, the middle is the model reconstruction, and then the difference is on the right. So just so you see how this went for this cluster model. Not perfect, obviously, which is why I said, and there's a paper with this, which has a list of things that could be done on top of this, but overall, this gave us some constraints on the time delay. I'm blinding for the moment the measured values. You can see pretty massive error bars right off the bat, 80 plus or minus 60, minus 20 plus or minus 30. But a couple interesting things here. So one is that, of course, the fourth image prediction is 7,700 days. So I think that one qualifies as a long time delay. But the thing that to keep in mind here is that there is such thing as too long, and I think we found it. So, yes, it's good to have a long baseline, but 20 years starts to border on, who's going to actually be around to look at this thing in 20 years. So, yeah, right. So, and also this one is demagnified, but not so much that I think, we could find it, but it is 15 years from now. Anyways, the other interesting thing is, we have one epoch of photometry here. It's clearly a transient. It's not necessarily a supernova, but the reason that this, we sort of went forward with this as a supernova is the lens modeled time delays here are not, while there are huge error bars, they are not like, 5 plus or minus 10 and 10 plus or minus 15. The relative time delay here, even with the uncertainties, is on the order of 100 days. But we see them all in this single epoch image. So the idea is that whatever the transient is, it's surviving for at least 100 observer frame days. So that cuts down a lot of the things that it could be, and we've gone forward with this analysis, assuming that it's a supernova. And it appears to be going forward. So long time delay, certainly, maybe too long. And then I'll just go into what we can infer from that one epoch of HST photometry. So the open circles here are the observed magnitudes we have Y and H band images, F105 and F160. And then the gray filled in images or shapes are the lens model corrected brightnesses. So the brightness that we would see if there was no lensing in the way. And then on the x-axis is color, and this analysis is completely ignoring microlensing because that would be really hard to deal with one epoch. And so in that case, the macrolensing says this is an achromatic lensing effect. So the x-axis is independent of any lens model. So basically, we did a bunch of simulations, including things like, dust distributions and, luminosity functions for each of these. And the idea basically became that, while each of these images could sort of be fit, you can see up here, like type 2 and 1BC are not, ridiculously off from this first image, but, none of them can really get as red as this is. In terms of the brightness, only a 1A really covers these. So overall, this is in the favor, but this ended up being, from the information we have, a greater than 90% chance of being a 1A, if it's a supernova. So taking all that together, we just assume it's a 1A from now on. I put it in parentheses because obviously it's not spectroscopic. But the idea is also that it doesn't really matter, because if you did wait 15 more years and come back and look at this, then certainly you'll be able to tell what type it is. And then you could just sort of redo this with the other model, right? So this is sort of like one way to possibly go through with this. And going forward, I think this is sort of an interesting analysis with this single epoch of data from a cluster lens supernova. What can we do with it? So here's our detection epoch from F105, F105 minus F160. So this is independent of a lens model because it's just the colors. And the idea here to get a time delay constraint is basically say, well, we see them all at the same time, but if we can get the age of the supernova in each image, then the difference between those ages is the same thing as the time delay. So for example, if we say, well, they must fit on some age axis, they fit somewhere along like this, then we assumed it was a 1A. So let's look at what the model looks like. And we just put a 1A model across the same time frame. And you can immediately see that what is actually image 2 is just way too blue to possibly be, 100 days old in the observer frame, or in 30 in the rest frame. And similarly, images 1 and 3 are just far too red to be, say, minus 10 days in the rest frame. So it was actually a bit lucky that these fell at these peaks, because it gave a reasonably good constraint with what we had. And so you can see this is your relative time delay. It's just the difference in age between the image 2 and 1 or 3. And you can do 1 and 3, but obviously they're very close together. So your constraint is very large error bars. You can do the same thing, including the lens model, to make sure that these agree. So if you, this is just the F160 light curve with 3 points, and correct each of these points using the best lens model magnification that we had, and then just do the same trick, okay? Make sure that the brightness matches up with some part of the light curve here. And if you do that, and I'll just flip back and forth real quick, you can kind of tell, yeah, these ended up in roughly the same place, which is reassuring. Both that the image 2 was at this early part of the light curve or color curve, and images 1 and 3 were at the later part. So great. So what did that end up looking like? Well, the ages that we measured were around 100 days for images 1 and 3, and then well before peak for image 2, which correspond to these time delays of 115 days plus or minus 30, and minus 17 days plus or minus 15 or 20 or so. And you can see that those agree pretty well, actually, despite the giant error bars with the lens model predicted values, especially the fact, just sort of qualitatively, that the delay between 2 and 1 is about 100 days, and the delay between 3 and 1 is negative, meaning that actually image 3 appeared first. So that's sort of the Requiem analysis, a lot done with very little data. So I'm just gonna put that behind us now and wait 15 years and move on to the Rubin and Roman Synergies component of this. So start very high level, just wavelength range. These are very complementary to each other. So you can see Rubin's got the blue end covered. There's a good overlap region, which is good for calibration purposes. And then Roman goes all the way out to 2 microns. So together, these will be quite nice. In terms of whether they'll actually have overlap, that's still up in the air. This is from Ryan Foley's original paper, but also was in Ben Rose's and et al.'s reference survey for the Roman high latitude time domain survey. And the 2 sort of like best candidates here are in the orange arrows. So certainly the Euclid Deep Field South, CDF South area would be good for coverage with LSST. And anything that is in this region, if say this goes forward, right? Anything that's in this region from Roman will have a full light curve for every lens supernova detection. Well, unless it happens to be one of the dropouts, but regardless, you'll end up with a sort of a wealth of data between LSST and Roman. And then going back to this for a second, our current sample will be significantly better. So this Rubin distribution, by the way, just want to mention, is the Oguri-Marshall 2010 distribution, and that has been updated since then, obviously with the WashTech 2019. But it doesn't really matter. It's actually the distribution that I care about most, not the total number. And the distribution in the 2019 paper ends up being about the same for the same assumptions. And the important thing is that obviously, while LSST is expected to find more, these are going to be relatively low redshift, sort of a tail out to the higher redshift range. There'll be actually a really nice overlap region with Roman, where you could imagine getting sort of a combination of data where Roman has the resolution, LSST has the cadence or something like that, and the blue end of the wavelength range. And then Roman will get all the way out to redshift 3 or 4 for this is source redshift, obviously. And so together, this will give us quite an interesting data set of lens sources covering essentially redshift all the way out to 4. So there's lots of interesting tests that we could do with that. And in the sort of high end of the Rubin redshift range, I'm going to sort of zoom in on this. So on the left here, first of all, you can imagine this is image separation with the Rubin PSF in a dashed line. And again, the blue is from Oguri-Marshall 2010, not the updated sample. And they cut it off here at some fraction below the PSF limit. So you could also imagine that there would be a bunch of blue unresolved points here, but that sample was just for resolved supernovae. So sort of up in here is interesting because there'll be a set of supernovae that are unresolved by Rubin but detected, and detectable and resolved by Roman with time delays that are, sort of greater than 10 days. So there will be some sample that is worth, say, TOOs from Roman or something like that, just to get the resolved image to then use the unresolved light curve from LSST for the time delays, because they are long enough that even a slightly higher time delay uncertainty will contribute a relatively high precision measurement for the Hubble constant. And on the right here, this is, I'll go back one second, is the lens and source redshifts. Again, you can kind of tell that these are sort of separated, but have a nice overlap region, which is it's the same distribution as we just saw. And then I overlay here. This is showing the Eric Linder showed earlier this plot showing the dark energy equation of state parameters when they have opposite, extra, they have like a interesting correlation at some redshifts when their dependence is on opposite sides of that, like derivatives as a function of the time delay equation plot. It's a little complicated, but the point is that there's extra constraining power in the blue region, which happens to be, all of the LSST range basically in this lens to source ratio space. And then there's a good chunk up here where Roman sort of takes over and gets essentially the rest of them. And so together, we essentially cover all of the area where the dark energy W0 WA space has this sort of interesting correlation that we can get this extra constraining power that came up earlier. Okay, I think that's, yeah. I just want to completely unrelated mention because of the rest of the week that, because I didn't talk about it on this because it has nothing to do with lensing at all, but for the LSST ZY band stuff, we have a new paper that it was just submitted that retrains the, well, Z through H band, essentially, that was the SALT2 extended, is now replaced with SALT3 near infrared, which is sort of a fully trained version of SALT. So anyone who's doing LSST simulations with either the Z band from SALT3 or the ZY bands from SALT2 extended can come talk to me about this, because there's a new model and a new paper that has a much better model for this. Okay, key takeaways from this. We should keep tracking this to see whether there's something more interesting going on here, or it's just been sort of luck of the draw from here up till this point. Rubin will observe many of them, and it's great for the fact that they have large angular separation, so they'll be sort of easy to do with Roman or with Rubin, and long time delays. But we got to be careful because they can get too long, and then they stop being so useful in the short term. And then we got sort of a surprising amount of info from a single epoch of Supernova Requiem. There's still interesting stuff to be done there. So, I don't think anyone is currently doing it, but there's updated lens modeling that could be done, as well as, trying to take this all the way through to cosmology, even with the terrible constraints that we have, giant error bars everywhere, but it would still be interesting to see if it could be done with a single epoch cluster lens supernova. And we'll see in 15 years for the rest. And then lens supernovae with Rubin and Roman, I think will be better in tandem than either one could be by themselves. So that'll be all. Thank you.
Thank you very much, Justin. Any questions in the audience or on Zoom? Maybe I start with the first one, with the supernova that you in your team, or you're part of the team, discovered. What would you have done differently if you had available resources to immediately follow up? Or
for Requiem?
For Requiem.
Yeah, I mean, so that is an interesting one, because we have essentially everything that we would need for it except the light curve, right? There's Muse data of the cluster. There's multiple bands of HST images. It's great. And I know there's one part missing from the lens modeling, which is there's already some kinematics measurements. But anyways, we obviously would just need more rapid follow-up for the light curves of the various images. So They're all there at the same time, so you'd actually wouldn't need that many resources. It's not like Refstall where we had to plan a year in advance and then come back and then do a whole program, right? So I think the point is just that if we had noticed that this was here in the first place in 2016, you got to be ready to trigger the follow-up on it, right? In a program like this, where it's not a cadence survey, we need to be able to discover it live and follow it up, which I think is still a part that's sort of lacking from where we are at in the Lens supernova community.
Just quick follow-up. So LSST would have done the job if it was online and overlapping.
Yes, right. We have everything else, that we would have needed, and even theoretically, maybe HST didn't catch it. We could have done like a Roman TOO or something to get that image, and LSST would have done the rest.
Hand it over to Graham Smith.
Hi.
Ooh, whoa.
Sorry about that. Hi again. Beautiful work. Nice talk. Can you say a little more about the outstanding lensing project that you mentioned? When we had Johan's mugshot on the screen. Interested to know more about that.
Yeah. So, you can also go look at the paper in the whatever extended materials, because it was a Nature Astronomy paper. They have the secondary materials or supplementary. There's a whole list of like things that we would like to have added but didn't, essentially. So one that had a lot of sort of referee complaints about that was there were some kinematics constraints that were not included in the lens modeling effort. We just sort of fixed it and said, this is what we're going to go with. But there was more data available that we did not use. And then there was also, we didn't do like a variety of, we just chose one parameterized model and rolled with it, right? So I think it would be great if someone would go back and, do a series of models, make sure that the various kinematics measurements are included. There's also, there was the Newman 2016 work on this cluster. And the results were a little different. We didn't really look into it that much, to be honest. So there's like a comparison effort to make sure that there isn't a systematic in one side or the other. So yeah, because it does matter for the magnifications of the individual images, which then impacts the classification and time delays and everything else. So there's a few steps there in the lens modeling that would be really good to go back to. And it is outlined in that paper. I think
Nikki Aronson.
Thank you. Can you say a little bit more about the new lensed supernova by the clusters that have been discovered, or is it still like classified?
I think I can. So these are both Pat Kelly and one of his postdocs there in Minnesota. The first one is another archival lens supernova. So another one of these where it wasn't caught live. So I think this is another contributing, theme of like, we're not really catching them live. So I don't know the year that one was, but I know that his postdoc has been working on searching archival data for lens supernovae using, some lens supernova transient detection algorithm, and found another one. So it's not live, and it's in the archive. And then the other one is, I think it's fine to say because it's all the DD stuff is public. He has a DD program, a director's discretionary program with HST, and is live now, but not necessarily multiply imaged. They're not positive, which is why, there's I'll send you there's an astronote on this, and the targets are live, but we've followed it with a few ground-based telescopes, and it was too faint, which I think ruled out it being a 1A at this point. And then it is also being followed up with HST right now, so we'll see what it comes to.
So slightly controversial, I guess. This completely unrelated Sol 3 near IR thing that you showed.
Yeah. I just want to pop that in because so for the rest of the week.
And you put the hook on the
Yeah.
fishing line and you caught the fish. So Rubin will find lots and lots of type 1A supernovae and has a Y band. And of course, supernovae are better standard candles as you go to the infrared. Is it better to have 5,000 regular 1As or 122 cluster 1As for W not WA? What's the trade-off? Well,
I mean, I think that you, in the end, want both, if you could, because of, they do complement each other, right? It's true still. But if I had to choose, yeah, I mean, I think 122 lens supernovae at this point would probably be more useful for at this point, because of, the database that we already have of 1As. And I think, having a new set of 122 lens supernovae would answer more questions at this point than 5,000 new 1As, but that's just me.
That's actually, it's good that you're taking a stand, because this is not as on desk radar, for example, for W0WA as the regular 1A cosmology case. So should you really want to advocate for that, we should probably put that on the science roadmap as a thing to do. So,
Yeah.
if you aren't involved in desk yet at that level, come talk to us. But also, one more quick thing on this. Both of these are going to use, both the regular 1As and the cluster 1As are going to, at some level, use the same model for a 1A for either getting distances or time delays. How do you actually model the covariance between cosmological inference with both these methods, since they're both ultimately using the same model underneath?
You mean in order to, if it's a 1A and you want to be able to do both?
Yeah. So
parts
if
with it?
both these methods for cosmological inference are depending on the same model, how do you deal with the fact that the model could be wrong?
Well, you can't really do both at the same time. In terms of, like, what I mean by that is you can use the SALT model, say, to measure time delays, for example, or you could use just some polynomial, right? It doesn't really matter. And so in that case, it's not the model itself that makes the difference. And then you could then use SALT or whatever model to do the standardization for a luminosity distance, right? But you could not use that as a lens model constraint and then also use it, to be a standard candle. Like, you have to choose one or the other. You can either fix it and let the lens model still have the mass sheet degeneracy, or you can try and fix the mass sheet degeneracy and then, not try to do the standardization. You can't go both ways. So yeah, but I mean, you could just not use one. I mean, you could use two different models. It doesn't really matter. It's just a choice of, there are enough models at this point that if you wanted to check to make sure you weren't making any mistakes, just use two different ones. Yeah.
This may be a silly question, because you may not care when you have 122 more, but 15 years from now, if I remember correctly, you had like a 3-year 1 sigma range on when that guy's going to happen. Do you have a plan for having a survey in place that's going to monitor often enough to catch it?
Yeah. It's funny.
This is going to be after LSST, LSST1 is over.
So I've put up a slide like this in a good few talks at this point, and that's the first time anyone's ever noticed how big the error bar is on that. I mean, it looks, you don't look at it because you're like, wow, 8,000 days, but it's over a year error bar on that. So it's true. So my hope, one, is that, as we were just talking about, that some more efforts will do the lens modeling and improve that. But it's unlikely that it'll get, to the point where we know it within a month, right? It's going to still be a year or something like that. So of course, no, at this point, there's no survey in place to do that. But I would hope to, in 13.5 years or something, put together a survey that checks that, at least, weekly or something, and just make sure that we catch it in the first week. It's going to be demagnified, so that's going to be a challenge, but it's also in 15 years. So who knows what resources will be available. But certainly it's an opportunity to catch it really early and, get some really interesting early data if we can do it.
Just a dose of realism. So let's go back in time 20 years. When was LSST supposed to start? Right. So if you're thinking a survey 15 years from now, you could probably already know what it is. I don't know.
Yeah, right. Yeah.
A perfect proposal for an extension of LSST, I would say.
Yeah, right.
Any other questions, comments? I see no one on Zoom. Then I would say let's thank Justin, Pierel again, and all the speakers of today. It was really great. For those on Zoom, well, no dinner plans or your own